Okay, we have been looking at, we've had our 2 lessons and we've looked at the general organic chemistry knowledge, looking at names, isomers, identifying compounds and all of that. We are going to deal with question 3 now, and that has to do with the physical properties of organic compounds. This one, quite easy to get your marks. It's very straightforward. So please get the notes right. Chemistry is so important and so pertinent on how you answer your questions. They want a particular system of answering, which I'll be giving you. So please, Term 1 exams are going to walk in very soon. So make sure you are following so that you don't have to do much of revision. Get the notes with me. All right, physical properties of organic compound. That is what we are going to be looking at today. Okay, so I have my notes from lesson 1 and 2, and I'm just going to move down to a fresh page. All right, we've covered quite some journey. So much. Yeah, chemistry is very voluminous, so understand why we have so many slides already. And after this, we'll have one more, which is to deal with organic reactions, and chemistry is done. Now, when we talk about physical properties, basically we are looking at boiling point and melting point. Okay. So we are looking at boiling point and melting point. That's what we are looking at basically. Melting point, boiling point. But before we discuss all of that, let's look at a few things. Okay, let me say boiling point versus melting point. And vapor pressure. Before we start, let's look at the definition of temperature. I know somebody's thinking how hot or how cold. That's the definition of a layman. Temperature. We need to know the definition. It is examinable. Okay, it is examinable. What is temperature? It is the average kinetic energy of particles in a compound. Average. Because not all of them would have the same energy. So when we add together and divide, just like a normal average mean, we talk about temperature. We are done with that definition. Quickly, temperature is defined as the average kinetic energy. Now we go to our main definitions. We are going to start with boiling point. Please don't write temperature at which something boils. You will be arrested. Boiling point. Let's define boiling point. It is the temperature. So I'm going to start racing now. Work with me and write as quickly as possible. Temperature at which the vapor pressure of a liquid. I'll explain vapor pressure as well. Vapor pressure of a liquid equals the atmospheric pressure. Please don't put it that atmospheric pressure is equal to vapor pressure. You'll be wrong. It is the vapor pressure that rises and becomes equal to the atmospheric what? Pressure. I want us to quickly define vapor pressure, this word. What is vapor pressure? Basically the pressure of a vapor. but we don't write it that way. Vapor pressure. What is vapor pressure? It is the pressure exerted by a vapor at equilibrium. That's a very important word. With its liquid in a closed system. The pressure exerted by a vapor. I'm going to quickly explain that. And this we experience every day, but we've never thought about it. This principle of vapor pressure is how your kettle, when you are boiling water, works at home. So your water boils and then switches off at a particular time. That switching off is controlled by the pressure. Let me quickly explain what my vapor pressure would be. So if I have a container, it must be closed. That's the idea. It must be closed. Okay, let me do melting point here. Let me quickly do melting point, and I'm going to explain something on the next page because I want to use a white background. What is melting point? Very important. We're supposed to know that as well. It is the temperature at which the solid and the liquid phases of a substance are at equilibrium. When something is melting, it's between liquid and what? Solid. So the temperature at which the liquid and the solid phases are at equilibrium. Boiling is from liquid to what? To vapor. And vapor pressure is the pressure exerted by a vapor at equilibrium. Now I want to quickly explain vapor pressure, and I'll be using that vapor pressure to establish something for us. The relationship between boiling point and vapor pressure. Let me know if we are done writing. I'm trying to be slow so that I can carry everybody along as quickly as possible. We need to finish this in the next 1 hour. Just give me a thumbs up once you're done writing. Awande, Unam, Karabo, Venusha, Untatile, Vukudo. All right, Fatima, you're also done. Zolunga. Kamani, you're logging in and logging out, probably network. Okay, Abdullah, I'm glad you're back. Lindo Kutle, you just joined. Lindo Kutle, you need to quickly take a screenshot. Those of you that just joined, you need to quickly take screenshots. What other people? Let me see. Who else do I have? Mr. Siwe, Kian, I'm glad you're in as well. Nell, beautiful. Teboko, lovely. Zahim, Zolunga, all right, great guys, great. Ibrahim, lovely, glad you made it. Those of you that are just coming in, please just take a picture. And by the way, these are just definitions. You have this. Your teachers have given you definition pages. Okay. Some of you have bought the cards, the definition cards. No, Kamani, I cannot get your reactions in this. But if you need to quickly learn about reactions, I'm going to send you a little clip. I've got about a 40 minutes clip own reaction that I can send you that you can, if you're writing before next week. Okay. Because I don't want to rush this. Yes, beautiful. Okay, guys, quickly, I want to explain something now based on temperature, boiling point, and vapor pressure. Now, in order for us to see what vapor pressure is, let me just change this. I need a white background. Let's see if I can get a white background. Then tools, I need to get my chemistry tools. Okay, just trying to be fancy, you know. Yeah, just trying to be fancy there. Beautiful. Well, let me use a beaker, not, I have a beaker there. Awesome. And we've got some fire. All right, I think this would do. I was trying to look for something covered. Oh, we can use a test tube. Awesome. Great. Okay, guys. So I have that's to give me heat because we're talking about boiling. Okay, I'm going to use, don't I need a stand? Okay, I'm just trying to be fancy, guys, just to make it look nice. Awesome. So, move to back. Great. Does it look like this thing is over it? Kind of. Okay, then I have a water bath. And inside this, I have my test tube. Okay, let's do this so we can see. Now, so you don't need any rocket science to see what is going on here. That I'm actually having a test tube and I have fire. Okay, why is this thing not covering? It's supposed to, yeah, that's what I need. Beautiful. Okay, guys, it must be closed. Please, it must be closed. Now, when I start boiling this, understand it must be what? Closed. When I start boiling, what happens? I start creating vapor. And because it is closed, what's going to happen? We are going to create pressure here. So all of this is vapor. This is why, yes, there's a hand there. Anybody, somebody talking to me there? Okay, I was wondering, a lady. Great. Okay. All right. So we have vapor there. Now, as the vapor increases, what happens? It starts creating pressure. Pressure starts building up, and that's why you see your lid bouncing. Lovely. Now, that vapor creates what? Pressure. The vapor creates pressure. And why is that? Why do we have pressure? Because it is closed. I hope it makes sense. It's just, you don't even need to go to school to see that. It's closed. Now, what is the relationship between vapor pressure and boiling point? My good learners, I want to ask you a question now. So, if I have compound A, and compound B, I've got to move now. And the boiling point of this is 20 degrees Celsius, while the boiling point of this is 100 degrees Celsius. Which one boils first? Your temperature is rising, okay? Which one boils first? Is it the one that is 20 or B, which is 100? Now, lady says A. I need a lot of answers. If you are lost, please let me know. Zolunga, why are you saying it's B? Why? The boiling point of A is very low. When the temperature reaches 20, it's already boiling. Compound B would need to get to 100 before it boils. Remember, temperature is rising. Zolu, are you okay with my explanation there? That A boils first. Okay, beautiful. A boils quickly. That is, it is converted from what? Liquid to vapor. Oh, it means we are going to have more vapor. There is more vapor in A than B at low temperature. And because there is more vapor, what happens? Vapor pressure increases because there's more vapor. Oh, so we can conclusively say that a substance with low boiling point, don't mind my flowers, will have a high vapor pressure simply because it changes into vapor quickly. Please let me know if it makes sense. If I were to have two test tubes, let me try to get two test tubes quickly. If I were to have two test tubes, all right, of A and B, this is A and this is B, maybe at what? At 20 degrees Celsius. This would have, this is already boiling. There's a lot of vapor here. Lots of vapor. But this one, it's not even, it's just check. I don't know if we are on the same page. It has to be closed, remember? Is this making sense to you? A changes quickly from liquid to vapor. So we create a lot of vapor, and because it's closed, we generate a high pressure, vapor pressure. Boiling point here is 20 degrees Celsius, and boiling point here is 100 degrees Celsius. And at 20, what do we have? Already A is boiling, B is still cool. You know, a quick way, just to make you see, it's just to make you, I want to create a picture. If you take a cup of water, put it in a pot, and take another pot and fill it with water, which one boils first? The small one. Here I'm not talking about volume, but just to make you see. The small one boils faster. It has more pressure than the one that is not boiling. It's still going to be cool. Let me know if that makes sense. A substance with low boiling point will have a high vapor pressure. Please, you didn't hear me say inversely proportional. Don't use that word. Not inversely. Please don't use the word inversely proportional. That's wrong. Okay, good. Now, let's go on. Factors that affect boiling point. Factors. I hope this makes sense. You can take a picture of this. Beautiful. I love the diagram. I love the diagram. Take a picture of this. Put it on your status and say hashtag crazy physics. Come on. Let's do that. Let's promote. Hashtag crazy physics. You know I have all your numbers saved. All your numbers are saved, so I must see your status. All of them. Now lady, you're laughing. All your numbers are saved, so I can see your status. If you don't post this and say hashtag crazy physics, you will see me. Okay. All right. But I hope my explanation makes sense. You know, it's just good to have fun. Factors that affect Did we get a picture? I don't want any. Somebody please take a picture of this, send to the group. Because somebody's going to say, no, I didn't take a picture. I want a picture on the group, and everybody take from the group and post on your status when we're done with class. Yes? A picture. Kamani. A picture. Naledi. A picture. I want it on the group. Mind you, I'm not going to continue if I don't see that picture, if I don't get a message. I'm waiting until I see the thing on the group. No image, no continuation. And if you don't post, I'm not sending you the link for the next class. Yay, thank you. Great, thank you Fatima. Thank you Ratile. If you don't post, you won't get the link for the next class. Okay. Factors that affect Yusreria, how are you? I'm glad you're in. Factors that affect boiling point. Quickly, I'm going to look at 4 of them. Factors that affect boiling point. And once I say boiling point, it will also affect melting point. Number 1, I am going to look at intermolecular forces, which is the common one. Intermolecular forces. Number 2, I'm going to look at molecular mass. Number 3, I'm going to look at the structure versus chain length. And number 4, I'm going to look at the position of the functional group. And we have 40 minutes to get that done. So we need to run. Intermolecular forces, that's the first one. We're going to basically look at 3 types of intermolecular forces. All right, we're looking at 3 types. Or let me just say type and the nature of the strength. Type and the nature of the strength. Oh, wait. I know you're drawing. Type. Where it is found, that's going to make it very easy for us. Sorry about, I know some of you have to clean. It's going to make it very easy. Type, where it is found, and then the strength. That would make it very easy. Type of intermolecular force, where it is found, and the strength. Without wasting time, London forces, or what you call Van der Waals. London forces. We find London between carbon and hydrogen. Please take note. We are going to find London forces. Anywhere I see carbon and hydrogen, it's a London force. Strength, very weak. And do you notice, once I say between carbon and hydrogen, where do you think we are going to find those compounds? It is found in all organic compounds, all of them, all. From alkanes to alcohols to aldehydes to carboxylic acid, every organic compound has C to H. So all organic compounds have London forces. All organic compounds have London forces. Dipole, dipole. I used to call it dipole, dipole. Dipole, dipole forces. Dipole, dipole. Where do we find that? We find that between carbon and oxygen, carbon and halogen. Please take note. Carbon and oxygen, and carbon and halogen. It is mild. It's not the weakest, yet not the strongest. Not the weakest, not the strongest. Where do you think we are going to find carbon connecting with oxygen or carbon connecting with halogen? All organic compounds except hydrocarbons. I don't know if it makes sense. All organic compounds except hydrocarbons. Remember, your hydrocarbons contain hydrogen and carbon only. So once I say all organic compounds except hydrocarbon. And number 3, hydrogen bond. That is between oxygen and hydrogen. Very strong. Amongst the 3, it is the strongest. Now, if you look at all your organic structures, where do you find hydrogen bond? You find it only in alcohols. And this one has one site. I'll explain it to you, but you don't need to know the reason, but you need to just have a knowledge. And number 2, you can only have O and H in alcohols and carboxylic acids. And this one has 2 sites of hydrogen bond. My beautiful learners, I am almost done with intermolecular forces. Just by this thing here, to know where it is found, we are done. Yes, talk to me. I want to take your questions now, lady.
So, what about in esters? Could we find it in esters as well?
No. Let's draw a quick structure of an ester, now, lady. An ester looks like this, right? If you remember. So what do you see? So what are you going to have here? In this, what are you going to have here?
We are going to have London forces.
Oh, you are so sweet, Nana. Hold on. London forces. What are we going to have here? In the middle there.
I think we're going to have dipole.
Oh, wait, now you're beautiful. Dipole what? Dipole. Remember, on the left hand side again, what do you have?
London forces.
Good. I hope this table now makes sense, guys.
Yes, sir. Thank you.
You are most welcome. Did this table make sense? All you need to know is where is it found, and you are done. Once you know where it's found, you're done. I only got 2 people that said it's okay. I'm not sure about the rest. That table just simplifies the whole thing. Now, how do I answer my questions? Can I move? I actually wish this structure, let me do something. I don't like the way this note is arranged like this because I drew this structure here. I would prefer something. Don't worry, it doesn't change anything. It's just me being, Oh, this is going to be a mission. No. Okay. I just want that diagram to be on the right and that table on the left. That's all I want to do. So nothing changes. Okay, while I'm trying to do sort my own thing here, I hope we are all okay. Okay, why is my mouse not showing? And I'm racing against time, but I want order. All right. Are my batteries dead or what? Okay, I don't have time. Let's move. Okay, you have the table and you have the diagram to let you see what's going on. How do I answer my question? Guys, we don't write stories. How do I answer my questions? Answering a question. Use bullet form. And the acronym I'm going to give you is called ICE. ICE. I created this acronym some few years ago and it's gone round. ICE. Number one, identify the type of intermolecular force. Identify the type of intermolecular force in the compounds. Definitely you are going to be comparing more than one. So you tell us in compound A it is what? Dipole. In compound B it is. Now I know some of you that have done this topic. This table looks very, very too elaborate for you. It looks too elaborate. And you are asking yourself, oh, I never knew that even alcohols contain, Alcohols contain London. In your head, you're just saying alcohols contain what? Hydroxy. There's a lot of you that are like that right now. And I want to create an analogy for you, a very quick analogy. When you leave primary school, you get a primary school certificate. Then you go to secondary school, you get your matric. Now, if somebody were to ask you, which certificate do you have? Are you aware that you don't tell people you have a primary school? You just tell them, I have a matric. But that's not the only one you have. But you downplay the primary school certificate and just say you have a matric. That is what's happening. We downplay the alkanes, we downplay the London force and say that what? Esters have dipole, but that's not true. For the fact that I have a matric means by default I have a primary school. So if something has a dipole, automatically it has a London. I don't know if it makes sense, everybody. And when I get to varsity and somebody says, what do you have? I say, no, I have a bachelor's degree in varsity, or I have my PhD. You don't say, okay, I have my primary school first, then I have my high school, then I have, no, you just go first to the highest one. This is why we say alcohols contain what? Hydrogen bond. But in the ideal sense, alcohol contains all of them. Because if you look at my table, you would find alcohols in the first, because alcohol is an organic compound. So alcohol is here. You will find it here because I said all organic compounds except alkane, alkene, and alkyne. That's my hydrocarbon. So there's alcohol here, and obviously, and if you can quickly look at the structure of alcohol, it would make sense. It has a COH, hydrogen bond, dipole, London. Can you see that? It's got the three. That's why it's very strong, because you have three forces. I hope that makes sense. You don't go back and fight your teacher. That's the whole idea. So people normally go for the highest. Now, lady, why are you laughing? You can punch your teacher tomorrow. No, Okay. But at least now you know the full details. Number one, identify. Number two, compare the strength. That's my C. Compare the strength of the intermolecular forces. And that's very easy. You know the weakest and the strongest, right? Number three, talk about the energy required to overcome, we don't break, overcome the intermolecular forces. Don't say break. We only break relationships, not intermolecular forces. And these are not relationships. You always fight your teacher. Now, lady, why do you always fight your teacher? Don't fight. Energy required to overcome. I'm just going to put a little note here. More energy is required to overcome stronger intermolecular forces than the weaker one. And that's just common sense, right? Than the weaker ones. Guys, when you compare, please mention both of them. Mention both of the forces. And use the word stronger than. Because you are comparing stronger than. Please, that is very key. The hydrogen bond in alcohol is stronger than the London force in alkanes. You are comparing. So please make sure you do a comparison. Comparison requires two things. I can't just come and say, guys, I am taller. Wouldn't you be waiting for the remaining part of the sentence? I say, guys, you know what? I'm taller. And they'll go like, Then, is that okay? I'm taller than my lady because I know she's short. Okay, I can't just say I'm taller. You have to finish the statement by comparison, by comparing. And finally, you can make your conclusion. That compounds with what? Strong intermolecular forces will have high boiling point and low vapor pressure. You conclude. You have all your marks. 1, 2, 3, 4. Done. ICE principle. Identify the type. You use that table for. Compare. You use the table. And then you tell us about the energy. The energy required to overcome this is more than the energy required. Bullets. Use bullet form. I'm done with intermolecular forces for now. Very simple, straight. It's 15 marks. This one here. In question 3. Let me know if we can move. We're looking at 4 points. We just looked at number 1. We just looked at number 1. Okay, everybody seems to be on my page and we are all done writing. You let me know if I need to come back. What is my number 2? Molecular mass. Beautiful. Now, molecular mass and chain length are quite, we can connect them. So I'm just going to connect both of them here. And make it 3. Molecular mass and chain length. They are connected. Why am I saying they are connected? As we add more atoms to a compound, the mass increases, so does the chain length. Let me explain that quickly. If I look at this, look at that. Anybody wants to give me the name of this compound? One second, I just want to check something. Sorry, just want to check something there. I said molecular mass. Okay, it's fine. If you can, just bring this here. Let's bring it here and then leave the structure alone. Okay. What's the name of this compound? Anybody? Thank you. Propane. This is propane. Now, let us add another atom of carbon. If I want to check the molecular mass here, carbon is 12 and hydrogen is 1. Do you want to calculate the molecular mass for me? It will be 12 times 3 plus 1 times 8. And what would that be? 36 plus 8. 44 grams per mole. That's the molecular mass. Should I then decide to add more carbons, just one, adding an extra carbon, my intention is to increase the molecular mass. But when I add carbon, do you notice that my chain length is now even longer? Because the chain length before was 3. Now chain length, let's write chain length here. 3 carbons. What? By adding another carbon, or it comes with its own hydrogens, and this is what? Butane. What is my molecular mass? 4 times 12, 48, plus 1 times what? 10. And that will be 58 grams per mole. Do you notice, my good learners? Chain length is now what? 4. Do you see that it has increased? 4 carbons. So the question is, how does this affect my boiling point? Let's see if I can squeeze it here. As chain length increases, and by the way, you know molecular mass is also increasing. Or let's put it the other way around. Sorry. As molecular mass increases, that will impact. Chain length also increases. Okay, how is that leading us? There are more points of contact of intermolecular force. Which makes the compound stronger. which makes the compound stronger. So where do we get the 12 carbon? How do you mean, Karabo? The atomic mass of carbon is 12, remember? From your periodic table. Is that what you mean? Okay. Atomic mass of carbon is 12. As you write, let me paint a picture of what I'm trying to explain here, guys. If you take a simple broomstick, do you guys know what a broom is? Some of you don't even sweep. You use a brush, or some of you use a vacuum cleaner. You know, this lazy generation. Do you know what a broom is? Let's see. Do you know what a broom is, everybody? A broom. You sure? Or do I need to show you a picture of a broom? Okay, if you know what a broom is, I want you to picture this. If I take just one strand, one stick, or just one, not the whole bunch, just one broomstick, I can break it easily, right? Lovely. As I add more, it's very weak, but as I add more of those, it becomes unbreakable. My mother used to, she used to give us that, I learned that first from my mother. She told me to hold just one stick broom, and I broke it with my finger. And she kept increasing it. Although it's weak, by the time I keep adding more, what happens? It becomes strong, such that you cannot even break it. So the more you have atoms added, you have more points of contact of intermolecular force. The net intermolecular force increases. So the compounds become what? Stronger. Making the compound stronger in terms of intermolecular force. And this increases the boiling point. Okay, let's add boiling and melting point, but decreases the vapor pressure. So the trick here is more points of contact. More points of contact. As my number of carbon atom increases, the chain length increases. More point of contact of the intermolecular force. And as that happens, the net intermolecular force of the compound increases, which makes it stronger. Are we okay here? Everybody okay? Remember, guys, I'm watching, I'm checking names. I need to make sure everyone is all right. So please don't feel that, you won't notice. I will. For example, Fatima, I don't know if you're okay. Okay, yeah, you see, I'll find out. I have a big screen here that is giving me everybody's reaction. Okay, we're good. Number 3, structure. Structure of the compound. Here we're going to talk about straight versus spherical. Straight chain. Yes. Somebody saying something there? There's a hand. I don't know. I just heard a sound.
So we can see.
You can't see my screen. Let's check. My screen is visible. Guys, can you see my screen?
So we can see your screen.
My screen is visible. Everybody's saying yes, they can. All right, let me help you. Go to the people in the participant. Oh, great. Okay. We are going to talk about straight chain versus what? Spherical. Yes, Kristen, your hand is up. Okay. Now, a straight chain. Okay, no problem. Now, when we talk about a straight chain, let me divide this. Here we're going to have what? A larger surface area. Those are the keywords. A larger surface area. Here, a smaller surface area. Due to what? Branches. The more branches we have, the more spherical the shape, the compound becomes. This is very important. For example, I can compare compounds and their chain isomers. All right, a compound versus its chain isomer. A parent compound versus its isomers. Let's look at a compound, for a quick compound, for example. Let's look at pentane. 1, 2, 3, 4. I hope you remember what isomers are. And if I want to do the isomer, I'll have 4. And I can go ahead and look at another isomer. Why are they isomers? Number of carbon atoms is the same, C5H12. This one is what? 2-methyl butane. This is 2,2. Please make sure you have 2 2's there. Dimethyl propane. But if you look at the shape, guys, if we were to draw a shape here, look at this. It's straight. Look at the surface area. But if I were to draw this, it is kind of becoming spherical. Right? It's no longer straight. And look at the last one. Can you see that that one is actually a lot more? That's what we mean. The more side chains it has, the more spherical it becomes. The more side chain it has, the more spherical it becomes. Now, I want to give us a note. Let me know if we are okay. All right. I want to quickly write the note on this one now. Which one has more? Unfortunately, I can't squeeze it on that page, so I have to go to a new page. Okay. straight chain, let's write quickly. Straight chain compounds have larger surface area. Which gives room for better stacking of compounds. This increases the strength of the intermolecular force. Of the compound. Compounds with more branches, or let's say compounds with branches, becomes spherical. The more branches they have, like we've seen there, I just want to give you the note. The more branches they have, the more spherical they become. The more spherical they become. The compounds, or let's say the atoms of the compounds are stacked over each other. Resulting in a smaller surface area. I want to give you a detailed note. And what? Weaker intermolecular force. Energy required is then low. Energy required to overcome the intermolecular force is small. Giving birth to what are we giving birth to? Low boiling point, but high vapor pressure. So it's all about the shape here. Let's write as quickly as possible. Sir, can we assume that the more side chains a compound has, the weaker? Yes, it's not even an assumption. And I think I mentioned it here. The more branches they have, the more spherical they become. Okay, are we done? We need to look at the last one, number 4. I feel like I want to say something here. Let me just put something here quickly before I go to number 4. When they are branched, just want to add this little light. When they are branched, no, but it's fine. Okay, when they are branched, the intermolecular force, please don't write IMF, write intermolecular force. It becomes shorter, right? Are weaker. And operate, this is why they are really weak, over short distances. Over short distances between one molecule and its neighbor. I don't know if it makes sense. The distance between them is quite short. That's why it becomes weak. The distance between them is short. That's why it becomes weak. Okay, quickly write that and we look at number 4. When we look at organic reactions, we're going to look at questions altogether of 3 and 4. Also, that one would not take time. Even that we had a break, we could have actually finished this because already we were done with this in 1 hour. Number 4 now. Are we good? Ready to go? Number 4. What did I say number 4 is? Position of the functional group. Or even the side, let's say functional group. Yeah, position of the functional group. All right, when the functional group, so here we're really looking at positional isomers, right? When the functional group is on the terminal carbon, and I want to quickly do a research on this with you quickly. The substance or the compound has a larger surface area as compared to when it is within the carbons. I'll give you a very good example. Let's look at this. Butane 1-ol. And butane 2-ol. Butane 1, and you can check, everything looks the same. They have the same intermolecular force, they have the same molecular mass, everything is actually the same. and it looks like there wouldn't be a difference. Can I ask you guys, somebody quickly check the boiling point of butane 1-ol, and somebody quickly, just Google quickly, and butane 2-ol. Quickly. I want you to do the research for me. Let's check. Just check for me quickly. Butane 2-ol is more spherical. Intermolecular forces are weaker. It's more spherical. Okay, if I say more spherical-ish, I'm now judging myself with what I told you. Then butane 1-ol. Because of the position. All right, because of the position of the functional group. It gives it a larger surface area. I don't know if somebody was able to check for me. A larger surface area than, I'm talking about, oh yeah, because of the position, okay. Wait, my English, my comparison, something is wrong. All right. Let's do that first point. Butane 1-ol has a larger surface area. That's so we don't get confused. Butane 1-ol has a larger surface area than butane 2. Just because of the position there. Therefore, what do we say? We have already spoken about larger surface area now. The intermolecular forces in butane 1-ol are stronger than that of butane 2. And we know, guys, we know the intermolecular force here, right? Hydrogen bond. What else do we now say? More energy is required. I'm done. To overcome the hydrogen bond. Hydrogen bond and London forces in butane 1-ol than butane 2-ol. Boiling point of butane 1-ol is higher with lower vapor pressure. But I want us to check. I need those values. Then butane 2-ol. Okay, let me just grab my phone and check. Oh, somebody has checked already. Great. Okay, thank you, Vernusha. Somebody also, okay, Mohammed also checked. Nalidi also checked. Butane 2-ol, 99.4. Check that. 99.4 degrees Celsius. Everything is the same. Molecular mass is the same. Is the same. Butane 1-ol, thank you guys, 117.7. Beautiful. Can you see that? 117. Everything looks the same. Everything looks the same, but look at the boiling point. I want us to try another one. Let's try a haloalkane. 1-bromo. Let's check 1 bromopropane and 2 bromopropane, if we can check that for me. But write the notes. Let me check, but because I want you to be also a witness. One boiling point, I'm okay, typing on my phone, boiling point of 1 bromo. One bromo. Let me use pentane. Let's check something. Okay, 1 bromo is 129 degrees Celsius. I don't know if somebody can confirm that for me. I've got 129. Are we done with this page? I'm done. I just want us to see values. I'm done for today's lesson. Done with boiling points. But I want us to see, but I want to mention something as well. Don't leave yet. Kian already jumped out because he said I'm done. Now he's going to miss this last point. Mohammed, what are you checking? 1 bromo. Oh, I'm checking something wrong. 1 bromopropane, you're getting 71. Okay, can somebody check 2 bro? Okay, let me try 2 bromo pentane. I think I typed something wrong there. No, propane. Yes, I see my mistake. 2 bromopropane boiling points. 59. I don't know if that makes sense to you again. Look at 1 bromo. 1 bromo. It's 3, right? Propane. You got 71 degrees Celsius. I typed in 2 bromo. Propane. And I'm getting 59. Do you see? Everything remains what? The same. Everything remains the same. If I quickly draw a structure, because it's sitting on my terminal carbon, it's different from when it's sitting in the middle. It becomes more spherical. I hope that and you can check a couple of other ones, you know. Finally, when doing comparison, it is only fair to compare 1 variable per time. Please, they are going to ask you to do some things. You cannot compare chain length and functional group. That's unfair. All right? So if you are comparing, you compare just 1 variable per time. This is what makes an investigation fair. This is very important. All other factors must be kept constant. All other factors must, underline must, be kept what? The same. You are only comparing 1 variable per time. For example, if I want to compare, if I want to compare this, this is what? Propan 1 or. I cannot, if I compare with this, this is not a fair comparison. Not fair. Not a fair comparison. I want you to understand what I mean. Why is it not a fair comparison? I am comparing more than 1 variable. I don't know if you can see that. It is not a fair, because I am comparing chain length and functional group. That's not fair. Not a fair comparison, because I'm comparing 2 things at the same. I'm cheating. what is that? Propan-1-ol. If I want to compare propan-1-ol, I should compare it with propanoic acid. Does that make sense? If I want to compare propan-1-ol, I should compare it with propane, propene, propine. I should compare it with anything pro. If I want to compare the functional group, OH, then I should compare if I'm comparing propan-1-ol, I can also compare it with butan-1-ol, because I have kept my OH on carbon number 1. These are little 2 marks that I need us to get. I can compare propan-1-ol and butan-1-ol. They are both alcohols, and the functional group sitting on carbon 1, I am comparing chain length. I don't know if it makes sense. Let me know, guys, if what I just explained makes sense. I am done. But let me know if it makes sense. Examiners are going to ask you, why is this a fair comparison and why is it not a fair comparison? Once you see that 2 things are compared, it is not fair. You have to compare one and keep the order the same. I could, for example, keeping the molecular mass the same, I could compare the chain length like we did earlier on. Pentane, pentane, 2-methyl butane, and 2,2-dimethyl. I'm sure you're done here. Just want to emphasize that. Let me just show you that quickly. When I was comparing here, oh, this is such a beautiful note. I love it myself. When I was comparing this, look at, are you aware that the molecular mass remains the same? Molecular mass. For all of them, 5 times 12 is 72 grams per mole. This one too, molecular mass, 72 grams per mole. This one too, molecular mass, 72 grams per mole. So that is my constant what? Variable. We don't just compare, we compare with one constant. That's it. I don't know if there's a question, but I'm done. One variable only per time. I am Donay. End of the lesson. Did it make sense to you? Are you good? Are you happy? More understanding from what you have already known? Okay. If there's no question, good night, everybody. Next lesson would answer a few questions. But good night, everybody, if there's no question. Yes, Naledi?
So, sir, if let's say we have pentane and we have propane, but we have a substituent that has 2 carbon atoms, could we say that's a fair comparison?
Sorry, say it again.
If we are comparing, let's say, pentane
yes.
and propane, but the propane has a substituent that has 2 carbon atoms, could we say that's a fair comparison?
Okay, Nana, when you say comparing what? Pentane and propane with 2 substituent carbon atoms, it's no longer propane. If I understand what you're saying, let me go to that page because I think we have it exactly here. Look, is this what you mean? Check. This is pentane.
Yes, sir.
Are you referring to, you said propane with 2 substituent that? Is that what you mean? That's not propane. That's not propane. That is 2,2-dimethyl propane. That is a very fair comparison. Why? This is the same. Do you notice? They have the same number of carbon atoms. What is the difference? There's only one difference: chain length. So it's a fair comparison.
Thank you, sir.
All right. Any more question? Yes. Amani? Sir, can you please help me with reactions when you're free? I'm writing it on Monday. Amani, I'm going to send you something just now, okay? Just now. I'll send it on the group. Somebody else might use it. All right, I'll send it just now. Okay, Nana? Awesome. All right, guys. Good night.